So a lot of this stuff for Unit 4 is going to rely on previous knowledge from Unit 3. So we're going to review some things in order for you to be prepared. You're going to need your periodic tables again. Periodic tables pretty much from this point on. Okay, so you might want to go ahead and get that out right now. Okay, so here's just a representation of the Bohr models. Remember, the Bohr models show you the basic energy levels, where the first two closest to the nucleus are the 1s. Remember, first energy level has the 1 sublevel, 2 electrons can go in it. Second energy level has the s and p, so that's why they have 8 in there, filling, because you fill 2s and 2p together, that's a total of 8 electrons. Then on these various elements up here, they're showing you the valence electrons in the third energy level or the second energy level, depending on which period you're looking at. Here, this one, period 2, lithium has 1 valence electron, beryllium has 2, a boron has 3, but it's following our regular valence electron system. Group 1 has 1, group 2 has 2, group 13 or 3a has 3, 14 or 4a has 4. Same thing here, 15 or 5a, the nitrogen group has 5, oxygen group has 6, halogens have 7. Most of your noble gases have 8, except for helium, remember, has 2. So keep that in mind. Gotta know our valence electrons because we have to be able to put them on dot structures, because that's going to be part of what we're going to be doing today. Now, Lewis dot structures. Used to represent the number of valence electrons. First, you write your symbol, like so. Example, carbon over here. Want to make sure everybody's writing them correctly too, so that you're going to be able to get the correct answers. Surround the symbol with the dots that represent the valence electrons. If we look at carbon, how many valence electrons does carbon have? What group is it in? It's 14 or 4a, so it's going to have 4. So we're going to put 4 dots and place them around the element, 1 on each side, like so. Remember, you put 1 on each side first before you pair anything up. Like if you get to group 15 with the nitrogen group where you would have 5, then you start pairing them up. Okay? So we're going to be using Lewis dot structures. We're going to start with that today, so I want to make sure that you're doing this correctly. Here are some more, another representation. This PowerPoint is on Blackboard for you, so you can go back and review it if you need to. But looking here, this would be representation of how to do them. Putting the Lewis dot structures together, 1 on each side here. C14, they all have 1 on each side. Group 15 here, there's the one that's paired. Okay, group 16 has 2 pairs, 17 has 3 pairs. And then, of course, the 18 there for neon and argon, they have all 8 around them. Okay? So let's take a look here. If I have an X with just 1 dot, what group am I talking about here? The first group, which happens to be what group? What are they called? Alkali metals, right? Okay, so if I was given this as a question, which one would this apply to? 1, 2, or 3? 1, sodium. Yes, that would be the correct answer. How about this one, where it has X with the 5 dots around it? Which one would that be? The 15 group, or 5A. So looking at our choices here, which ones would that apply to? 2 and 3, because both nitrogen and phosphorus are in group 15 or 5A, so they'd have 5 dots each. So those would be some examples identifying Lewis dot structures. Remember, we're doing this because we want to satisfy the octet rule, and the octet rule, full octet would be 8 for most elements, so that they all look like they're nearest noble gas and have that noble gas configuration. Remember, that's about stability. Most atoms have to bond in order to find that stability. We're going to be looking mainly at ionic bonding today, but we'll be looking at covalent bonding later on in the unit. All elements want to be like their nearest noble gas because that provides stability, but most atoms have to achieve it through some sort of chemical bond. How do atoms do this? They form chemical bonds. So chemical bonds are the strong forces that cause them to stick to one another, so they have a noble gas configuration. We're going to be looking at these 2 ways today. We won't really be paying too much attention to metallic bonding, although you saw that in the previous notes, and you have your previous notes on bonding. There's also that PowerPoint that you can go back and review, but we did that before the break So you're probably going to need to go back and look at it. A lot of us have forgotten information from that far away ago. Ionic compounds exchange electrons. One transfers, one loses, one gains. And that exchange allows them to form ions, and ions a positive and a negative. And then from the positive and negative, they get this electrostatic force, this Coulombic attraction. That electrostatic force, the positive attracting the oppositely charged negative, glues them together. That is the chemical bond. The transferring of electrons is not the chemical bond. It's the positive and negative attracting to one another that makes the chemical bond. Without the transfer, though, you don't have the chemical bond. Covalent or metallic bonds are sharing electrons. Electrons are kind of, for metallic bonds, they're that sea of delocalized electrons spread around. They're, like a sheet of aluminum foil, just a bunch of aluminum atoms. But they are sharing those electrons, the delocalized ones, around the different nuclei. Covalent, though, they're actually sharing them between two separate atoms. Okay, and the two nuclei and the electron clouds being attracted to each other's nuclei, and all of that comes into the sharing part for covalent. We're going to focus on covalent, though, in the latter part of the unit. So, strong bonds form when electrons are exchanged. Remember, it's a metal and a non-metal. The metal is going to lose electrons and form the cation. The non-metal is going to gain electrons and form the anion. Positive attracts the negative, and that's why these guys have high boiling and melting points, because they're really strong forces holding them together. To get them to melt or boil takes a lot of energy. We're talking thousands of degrees, especially for boiling, melting. To melt sodium chloride, what we put on our food is, somewhere in like the 800 range. It's very, very, very hot. All ionic compounds are called salts. That is a class of compounds that has a metal and a non-metal forming the compound. We call sodium chloride salt, but really anything that is an ionic compound is also falling into that category. All right, so now we're going to go back to the drawing part. So we're going to start here, look at this particular example. If I wanted to draw sodium chloride, which we did also in the other PowerPoint, you can go back and review. One dot for sodium because it has one valence electron. The chlorine right here has 7 valence electrons, so it has 7 dots around it. But what the sodium does is it gives it up and forms an Na+. The chlorine now gains it, and it has 8 now around it with the -1 charge, and because they have positive and negative, they are now attracted to one another. That electrostatic force is called a Coulombic attraction. Not that important, but that's why they build these lattice structures. See the lattice structure here? Where it's a repeating pattern of positive and negatives and positive and negatives. This one happens to be very cubic in its nature. Not all of them are cubic. Depends on the ratio, like it could be a 1-to-2 ratio, a 2-to-3 ratio, but they form geometric different patterns in their lattice structures. Remember, it was like the Tinker Toys examples where it looks like they're a repeating pattern over and over again, building this big cube. Okay, that's what we're talking about, the lattice structure. So now we're going to practice drawing these, and I'm going to go ahead and pull that up, get out 2 colors so we can go over the example, and I can show you exactly what I want you to do here. Okay, so looking up here at this particular example, I give you the example of the aluminum oxide shown here. Now, in each problem, before you begin, it shows you right here, Al2O3, it tells you the chemical formula. It tells you how many of each atom is in this chemical formula. Al2 means 2 aluminum atoms. O3 means there's got to be 3 oxygen atoms. So when you're drawing this out, make sure you have the correct number of atoms of each before you begin. So here, since we need 2 aluminums, we drew 2 aluminums here. That's the first step. Draw the 2 aluminum, put the symbol down. Then you add the dots with respective to the valence electrons. Each aluminum, because aluminum is in group 13 or 3A, is going to have 3 valence electrons. So I put 3 blue dots around each aluminum. Now, because the chemical formula tells me there's 3 oxygens in this ratio, I write down the 3 oxygens. And I put the 6 dots around each oxygen, because each oxygen brings 6 valence electrons to the party here, to the compound. So put 6 dots, I did them in red, so as you can see. Then you're going to draw arrows. So this is what you would be doing underneath the compound chemical formula. And then over in the box, using your 2 different colors, you're showing me the new charge is formed. And by having 2 colors, you're showing me which dots came from the original atom and which dot came from the one that transferred. But you also have to make sure that each particular atom gets its charge, so that Al, each one of them is losing 3. 1, 2, 3. So this one gets a +3 charge. This one is also losing, that one would go up here, this one goes down here, that one can go down here. So each aluminum loses 3 electrons. They both end up with a +3 charge, so you must attach a +3 to both aluminums. Here, the oxygens, each oxygen is gaining 2 electrons. So, and we put them in blue because those are the ones that came from the aluminum. But then you must assign the -2 charge there because each one gained 2 electrons. So each oxygen ends up gaining that charge on there, so don't forget to write that down. Let's do one example together, and then I'll have you do, spend some time doing, working on this. So if I'm looking here at this Na3N compound, how many sodiums should I write down? 3. And pick one color, to use. Na, Na, Na. I'm going to write down 3. How many valence electrons does each sodium get? It is an alkali metal. It's in group 1, so each one gets only 1 electron. 1 dot each. Now, how many nitrogens are in the compound? Only 1, so I put 1 here. And I'm doing this all underneath the chemical symbol because to the right I'm going to put the finished product. Looking at the nitrogen, how many valence electrons is it going to bring to the gate? 5. It's in group 15 or 5A, so it brings in 5 dots. So we'll put 1 on each side and pair it up, like so. Now I want you to draw the arrows showing the transfer. Sodium is transferring electrons. Oops, my arrows are a little bit off. Here, let me try this again. Let me make this one up here. I'll have it go around. We'll make that one go around over here to that side. Okay, show the transfer with the arrows, like so, to one of the open spots around the nitrogen. So this is all, this work part goes under here. Then over to the right, I'm going to put in the finished product. Now each sodium is now missing an electron, so what's the charge on each of the sodiums? They just get a plus or a +1, but remember you don't have to put the number if it's understood 1. So we put the 3 sodiums all with the +1 charge over here, and the nitrogen now has some red electrons around it because the red electrons came from the sodium, but it gained 3. So what does the nitrogen's charge turn into? -3, and now it's called nitrite, so we would put a 3-. So that's how I want to see it. Over here, draw them before the transfer. In the box, show them after the transfer with their charges. So go ahead and take a moment and try a few on your own. To now, some formula writing. Okay, so ionic dot structures, hopefully you got the rhythm of drawing them and showing the transfer and showing the new charges and things. Formation of the ionic compound, this is another example of that. The formula unit is the ratio established between. So, for example, the calcium, we need 2 atoms of fluorine here in order to make this work. So we add another fluorine so that it can transfer that electron. But ultimately, what happens here when we get our Lewis dot structures drawn, we have 1 calcium for every 2 fluorines. So the chemical formula ends up being CaF2. And this is the formula unit. You heard that word before when we were doing Avogadro's number, but formula unit is the lowest ratio of the repeating pattern in the ionic compound. So that 1Ca2S is going to repeat over and over again, building a lattice structure. So when we write the chemical formula for an ionic compound, we're really just writing the lowest ratio of the repeating pattern. Okay? And over here I wrote over this part, so let's read it. The calcium wants to lose the 2 electrons, the fluorine needs to gain the 1 electron, so we end up with this 1:2 ratio, CaF2. The Criss-Cross method. This is what we're going to be doing on the opposite side. So I'm going to show you how this works. It's a quick, easy way in order to write chemical formulas. But you need to know your charges of your groups, so that's why you have your periodic table out. So looking here, we have aluminum and oxygen. So if I look at the group aluminum, it's in 13 or 3A. That group is going to be +3. Oxygen group 16 or 6A, that's a -2 group if you're following the charges of the group. Now, the charge number, not the charge itself, but the charge number is what's going to crisscross. So the aluminum, the 3 is going to go from the aluminum right here down here to the oxygen and become the oxygen subscript. The 2 right here is going to become the subscript for the aluminum. And we're going to be able to establish quickly the correct ratio to get the charges to add up to 0. So the chemical formula for aluminum oxide is Al2O3. Okay? So that is a quick, easy way to do it. However, there is sometimes a snag. This is how you need to look at it. Barium is +2 because it's an alkaline earth metal. Oxygen is still oxide, which is -2. But if we crisscross these, look what happens. It's Ba2O2. And in order to be a formula unit, it has to be the lowest ratio. Is that the lowest ratio? A 2 to 2 is not a lowest ratio. We need to make it what?
BAO.
1 to 1 in BAO. Correct. So this one is going to reduce. You would reduce it down to its lowest ratio, and it would end up being BAO. So now on the back of what we were just working on, we have a chart to fill in following the Criss-Cross method. So let's go ahead and take a look at some of those examples. Okay, so looking up here, we're doing the example. Say they just told me strontium oxide. They didn't tell me this part over here. They didn't let me know what the charges were or anything. What I would do if they just gave me the name is I'd look at strontium on the periodic table. Where is strontium on the periodic table? It's an alkaline earth metal, so we're going to give it, we would write out the symbol, Sr2+. Then I would look up oxide or oxygen on the periodic table and figure out where it is located, its charge. It is in 16 or 6A, so it's going to have a -2 charge. Now what I was going to do is I would crisscross. Okay, so the 2 here is going to be the 2 on the oxygen. The 2 here is going to become the 2 on the strontium. So yes, it ends up being Sr2O2. But we know we have to have the lowest ratio, so this one would reduce down to what? SRO. Very good. Okay. So let's look at the next example, and then we'll try some in the chart. You do not need to write the subscript 1, though, for a subscript, because if you just have the element symbol there, it means it's an understood 1. Okay? So iron 3 sulfide. Now we're going to go over what this Roman numeral means. It actually means that the charge on the iron is going to be a +3 because iron is a mom. It's a multiple oxidation metal. So it has more than one charge possibility, so we put Fe with the 3+. Because we know the charge on the iron this time happens to be a 3. Now for the sulfide is -2 because it's in the oxygen group. For this case, the 2 now is going to crisscross and become the subscript on the iron. The 3 is going to crisscross and become the subscript on the sulfur. So when we write out the final formula, this becomes over here, this goes over here, we get Fe2S3. Is that the most reduced ratio? Yes, so we would leave it just like that. Let's try a couple in the chart, and then I'll let you guys do the rest of the work on this. So if I'm crisscrossing sodium with this phosphide here, the P3 minus, the 1 of the sodium is going to be on the phosphorus. The 3 on the phosphorus is going to be the subscript on the sodium. So crisscross it down, Na3P. Crisscross. 3 goes on the sodium, the 1 goes to the P. It's an understood 1, so we don't put a 1. All right, for the next one, the next example here. We have Na is going to get a what? It's going to get the 2 because the sulfur here has a 2. The sodium gives the sulfur a 1, so it's just going to be Na2S is the chemical formula. So for this particular ionic compound, you're going to have 2 sodiums and 1 sulfur to make it work. That's going to be your formula unit or lowest ratio. Let's do one more line together. How about, say, this iron one? Iron 2 in this case, this is where it would have a Roman numeral of 2, because in this case the iron holds a 2+ charge. So when I cross it with chloride, what's going to happen here? The Fe is going to get a what? A 1, so we don't really write it, but then the chlorine gets a 2, so it's FeCl2, crisscross. Now let's do the next one with the oxide. What is that? What happens there? They're both 2's. Please don't throw things. +2 and -2 reduces down to 1, so it should just be what? FeO, like so. How about the next one, the iron with the phosphide this time? Fe with the 3, good, and the P gets a 2. And last but not least, with the sulfide, iron 2 sulfide, it's just going to be Fe what? S. They're both going to reduce down to 1s, and therefore will give you the formula unit of FeS. Now please go ahead and take some time and work on that. And I'll give you some moments, and then we will resume in a minute. Okay, so let's take a look here at naming stuff. You did a little bit of it when you were using the pieces in that activity. Here we go. Naming compounds, the metal cation is always going to be the same as it appears on the periodic table. So calcium is calcium, sodium is sodium, iron is iron, okay? 2 types of cations, though. Remember, we have our ones that have a single oxidation number, a single charge, and then we have our multiple oxidation metals, the ones with 2 or more. Remember these guys, the 2 or more ones, we call them MOMs, are multiple oxidation metals, and you need to use a Roman numeral with them, because how will we know which one you're talking about if we don't have a number to indicate? So if we're talking like here, copper with a +1, that's going to be copper 1 with Roman numeral 1. Copper with a +2, then you would use a Roman numeral 2. So just to refresh people's memories of Roman numerals, if you haven't done them in a while, remember 1, here's 2, 3, 4 is the 1 before the V, 5 is the V, 6 is a 1 after the V, 7, 8 has 3, 9 is 1 before the X, and then X is 10. Now, I seriously doubt you're going to need to go higher than 7, because manganese has a +7, chromium has a +7, but most of them stay way below, and they're usually 1, 2, or 3 in terms of their charges, maybe occasionally a +4. But for the most part, this is the Roman numeral system. If you don't remember it, you can write it down. So just to reiterate, this one is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. Following the Roman numeral system. If you need to write those down, that's great. If you already know them, that's fine. Okay? Now, let's look at some of these examples here. Anions. Remember there, you did this already. You changed the POGL. You looked at this. You changed the ending to IDE. Example, oxygen is no longer oxygen. It becomes oxide. Common one is carbide, because carbon changes to carbide. Nitrogen changes to nitride. Oxygen becomes oxide. Fluorine becomes fluoride. That's what's in our toothpaste and when we go to the dentist. Phosphorus becomes phosphide. Okay, so this is how you would note them Anions, the nonmetals, always change to the IDE ending. Okay? The IDE ending. Okay? So keep that in mind. All right, the cation always is first, the metal always is first in the chemical compound and in the name. It's always going to be written first. The anion or the nonmetal is always going to be second in the compound for ionic compounds. So here, looking at this particular example, this is doing it a different method than the Criss-Cross method that we just did. The aluminum is +3, the oxygen is -2. So I can multiply them in order to get a common number, like here. This ends up being +6, this ends up being -6, and so they have to add up to 0. Okay, so I can figure out the chemical formula by multiplying them in my head. And then I get my chemical formula, Al2O. Now, aluminum is not a multiple oxidation metal. It's in group 13. It always goes to +3. So to name it, I would just write the word aluminum and then oxide for the oxygen. So the name of Al2O3 happens to be aluminum oxide. No Roman numerals needed because aluminum only has one oxidation number or charge. Remember, the only elements that you're really going to be finding that have the more than one oxidation number are usually in the transition metal section, the D block, and lead and tin. Okay? Those ones are going to be the ones that you're going to see that have Roman numerals with them. Okay? So this is how you could balance the charges this way. You could also use the Criss-Cross method. That's also something that's possible. So now for naming, complete the names of the following binary ionic compounds. So if I have Na3N, it's sodium what? Nitride. The nitrogen changes to nitride. Okay, good. How about this? KBr. K is potassium, so we don't change that, but Br becomes, it's not bromine anymore, it's bromide. Very good. And we just did this one, aluminum oxide. And last but not least here, it didn't give us either of the names. Mg is going to be represented with magnesium. And then S turns into sulfide. Sulfur turns into sulfide. Very good. Like so. All right, here. What is the charge on the bromide? Bromine is a halogen, so halogens are, and so yes, it's a total of -2. So what does the iron have to be in order for it to be 0? This has to be +2, right? So we add those up, the iron has to be a Roman numeral 2 there. This one's a little tricky. What is our charge on our oxide? No, it has 6 valence electrons, so what is its charge? -2. Now there's 2 coppers here, and the 2 coppers together have to add up to +2 to make this equal 0. So what is each copper worth then? Each copper is only worth a +1, right? Because then we have +2 and the -2, that adds up to 0. So each copper is only a 1, so our Roman numeral would be a 1 there. The Roman numeral identifies the number in the charge, don't forget. This one we looked at on the previous page with fluorine, but there's 4 chlorides at -1, so the tin has to be a what? +4, so this would be tin, 4, chloride. How about this one? Oxygen is -2. And there's 3 of them, so this is a total of -6, right? There's 2 irons, and the 2 irons must add up to +6, right? Because this needs to equal 0. how much is each iron worth? They have to add up to +6, and there's 2 of them. How much is each worth? So they're +3. So this has to be iron 3 oxide. And last but not least, this one. What's the charge on the sulfur? -2. So in this case, the copper has to be a +2 in order to add up to 0. So this is going to be copper 2 sulfide. Okay? So that's how you do it, looking at the charges. So you can see the full answers. There you go. Make sure you have the correct notes and finish up those worksheets for homework.